Hanson. So Eve is the lead for industrial sectors at Third Derivative, which is a program jointly operated between RMI and New Energy Nexus. And she's been researching in particular DAC 2.0 or 3.0, like next generation direct air capture. Without further ado, Eve, the floor is yours.
Thanks so much. Well, first off, thank you, Ben, for the invitation. Thanks to all of our panelists for the great subject today and all the attendees. I think what we've heard today is that this is an all hands on deck sort of situation. And so very much looking forward to engaging with folks further after this. So today I'm going to give a brief sort of introduction presentation to direct air capture, or DAC. My goal with this 15-minute presentation is for the aspiring entrepreneurs and innovators in the audience to get a sense of where in direct air capture are we seeing the highest leverage points, the biggest opportunity areas for new technology, new innovation to really be that DAC 2.0 or DAC 3.0 and help make this technology scalable to the scale that we think we may need given the scale of the problem of carbon removal. Okay, so first, I'm going to start us off with some introductions. So first, Third Derivative, who are we? We were founded by Rocky Mountain Institute and New Energy Nexus, and we are a global climate tech startup accelerator with the mission of building an inclusive ecosystem to find, fund, and scale the most promising climate tech innovation and startups. So, we think that the climate crisis is a $1 trillion challenge and opportunity, and that we need equitable and global innovation in order to meet that challenge. And we are now on cohort 419. We have 62 total startups spanning every major greenhouse gas emission sector, comprising the world's largest cohort of climate tech startups. A little bit about me. My background is technical and commercial. So my training is in chemistry and material science. I got my PhD at Northwestern and have been bouncing around kind of consulting investment in the climate tech game here for a while, including my own stint at a VC-backed startup called Citrine Informatics, where I worked on materials informatics and stood up the customer engagement team. My role now at Third Derivative is I lead sourcing and diligence for all startups across the clean industrial sector. And as Benjamin mentioned, DAC is an emerging priority area for us. And this is a little teaser that we have our annual summit next week. And we have some exciting announcements in this area. So I really hope that folks can join. And I'm going to be sharing materials today from an upcoming publication that we also are going to be publishing around next week. All right, so let's start with some definitions of terms and what are we actually talking about with direct air capture. So as we maybe alluded to earlier in the panel, this is in contrast to point source capture. So point source carbon capture technologies capture CO2 from industrial flue gases, whereas if you're focused on negative emissions, carbon removal, then we're talking about direct air capture, where we are literally trying to capture the CO2 back out of the atmosphere. And so that's capturing that 0.04% or 400 ppm from the atmosphere all around the world. There's 3 typical steps in a direct air capture system. So we have the air contactor. So this is generally massive fans that blow air across so that you can get in contact with that very dilute concentration of CO2. Then there's an acid-base reaction where you have a basic sorbent or solvent to capture that CO2. And then a regeneration step where you release the CO2 to then use it or sequester it. And then you have that solvent or sorbent available again for future CO2 capture. All right, so just to put this in context of the various CDR solutions that we've heard about today, direct air capture really has the benefits of having long duration storage if you couple it with geologic storage. It has this advantage of being more permanent, lower risk of reversal, but it's still very early days. And so this is just a taxonomy from the Oxford Principles to give a little bit of color as to where this fits. But I've seen in the chat today a few questions to the effect of which of these solutions is best. My personal opinion is that given the scale of the challenge that we're talking about, 2 to 20 gigatons of CO2 removal per year, this is going to be a portfolio approach both based on all the different technologies that we need to bring to bear that we're talking about today. And even within direct air capture, this isn't going to be a winner take all market. This is going to be a portfolio of technologies that we need to build and innovate and then scale in order to meet that billions of tons per year challenge of removal. So a couple pros and cons of direct air capture. It has a bit of a lightning rod reputation, so I wanted to call this out up front. Pros: geographically flexible. Our atmosphere is everywhere, so you can capture CO2 from the atmosphere pretty much everywhere. That means that you can be more distributed and potentially co-locate with where you want to sequester that CO2. Climeworks has a nice example of that with their Iceland pilot facility. It tends to be more bipartisan. So in the latest infrastructure bill passed by Congress, that in the United States, there's over $3 billion, 3.5 dedicated towards direct air capture. So there's that advantage. And again, it's amenable to this permanent storage. Cons: it's a tough thermodynamic challenge to think about capturing that very low concentration of CO2, especially versus kind of legacy point source, which even in itself has had some trouble with performing to kind of the specs of the target CO2 capture rates. Once CO2 is captured and sequestered, again, you need to store that somewhere. And right now it's very energy intensive. And so what that means is it's currently quite a bit of electricity, and then also sometimes often thermal heat, which can include fossil fuels like natural gas. And I think we touched on this already, but the moral hazard is very real. So I want to very strongly emphasize that this is not an adequate solution on its own, and that we need to aggressively pursue emissions reductions, which my colleagues at RMI are pursuing through a variety of work that we do, and that this is in some ways the necessary addition, given that we already are at 1 degree warming in 2021. Okay, so where are we today? We're in very early days. So if you look at all of the combined capacity of the pioneers of DAC 1.0, if you want to call it that, of Carbon Engineering, Climeworks, and Global Thermostat, so that total installed capacity is about 10,000 tons of CO2 removal per year. Again, that's in comparison to 1 billion or 10 billion tons a year that we're looking at meeting. This energy requirement is very high. So across these different approaches, we're talking about 7 gigajoules or more per ton of CO2 removed. To put that in context, if you were to remove the CO2 from a typical car, which is a few tons of CO2 released per year, the equivalent DAC energy you would need to capture that would be the energy that would power an average home for a full year. So this is quite energy intensive. It's quite expensive now. Costs right now are $500 plus, but there's hope. We've talked about learning curves a bit today, and the company projected cost floors are down to $100 to $300 a ton. So this is taking into account the improvements in costs that these companies expect based on scaling up to 1 million tons per year capture or more, based on learning rates, economies of scale, etc. All right, so what we did here is there's a really nice analysis from a National Academy of Sciences report that came out in 2019 that gave ranges of estimated cost projections of the leading current technologies at 1 million tons per year scale. And so again, because these are all projections versus the very small base that we have today, I want everybody to take this with a grain of salt. But what I do think is instructive is to look at the breakdown of what are the biggest sources of cost in these current technologies, to also kind of flip that on its head and see where are the biggest opportunities for innovation. So if you look at the liquid solvent or solid sorbent cases, for the liquid solvent case, the biggest cost driver is CapEx, and in particular, those massive fans that we were talking about, the air contactor. Whereas for the solid sorbent case, the biggest cost driver is that sorbent capture agent itself. And then across both, energy, because it's so energy intensive, is a massive driver of cost. So if you as an innovator or technologist are thinking about, hey, where should I focus if I'm going to go in the lab? The answer is that air contacting, the sorbent cost, and the regeneration energy. And I'm going to talk about those in a little bit more detail, each in turn. All right, so for air contacting, for the liquid solvent case, this can represent up to 1/4 of the overall cost of capture. Carbon engineering has really done a lot of the leading innovation in this space because it represents such a large part of their cost stack. They've already dropped that cost by tenfold by using cheaper materials, using computational tools to optimize the air contacting and pressure beds for, or the contactor beds for the particular chemistry that they're using. And so, again, there's tools to learn from their leadership in the space around how to apply that for new chemistries. And then there's another concept called passive air contacting, which is just a fancy way of saying using wind, natural airflow, or existing airflows to move the air to then capture the CO2. So that's folks like Heirloom or Noya, who's looking at using, sitting on top of buildings' existing HVAC systems so that you can just leverage the existing airflow that you already have. I'm going to talk a minute about solid sorbent design because I think this area is particularly ripe for innovation. So there's a couple of benefits for using these solid sorbents. One, these systems can be fully electrified and coupled to renewables, which is very important when you're thinking about negative emissions. And what we did is we took sort of a sensitivity analysis. So if you take these middle of the road cost assumptions for solid sorbents, and then look at what are some frontier values if you improved the lifetime of a sorbent, made it a lot cheaper, made it cycle quicker or have higher capacity, what are some of the implications in terms of the overall cost of CO2 capture with assumptions around energy cost? And so with some aggressive, but not, but sort of within the realm of possibility improvements in some of these sorbent characteristics and with existing renewable pricing, you can get down to about $100 a ton. And then if you make some assumptions around lower energy from renewables, then this all of a sudden becomes a lot more attractive at things like $60 a ton. So again, we'll be publishing on this, so you can dig into all the details, but I think this is exciting to give a sense of the realm of possibility based on innovations in the area. And then I think I've mentioned several times already that a key challenge here is that regeneration energy. It's so energy intensive. And so new approaches are looking at lowering that regeneration energy either by targeting more specifically the heating of the sorbent material versus the overall chamber, the specific binding energy of that CO2 to the sorbent through targeted energy like microwaves, and things like electrochemistry. And so one of our portfolio companies is Mission Zero is one example of this, but there's a variety of folks who are looking at how do you bring this regeneration energy down using electrochemical approaches. And so I've put out a couple targets of things that we like to look for in startups that are attacking this space. So because we have a technical group and folks who are thinking about working in this area, I wanted to leave you all with a DAC Innovation Wishlist. And so if you're thinking about what are targets for really a best-in-class DAC 2.0 system, it's lowering that energy intensity, having an ability to be fully electrified and coupled to renewables so that you are not re-emitting CO2 as part of your CO2 capture, having that path to low cost, being more modular with off-the-shelf parts, which lets you demonstrate your technology more cheaply without kind of that $1 billion plus of capital that Clea was alluding to earlier from traditional CCS. And then because, again, we're talking about gigaton-scale capture, we have to be mindful about the footprint. So making sure that sorbent is safe, cheap, and abundant with limited social and environmental impacts, that the physical footprint of the system doesn't compete with other important priorities like food, and that we're keeping an eye on the water consumption and scale. So a few calls to action if you want to learn more. We do have our summit just coming up next week, so highly encourage folks to join us for our public day there. And then we are continuing to accept applications and accept new startups into our cohort. So definitely encourage folks to apply if you're working on relevant systems. Thank you.
Thank you so much, Eve. That was amazing, super interesting. So we have a couple of questions on your presentation. So we have a question from Robert, who asks, how do you view the risk for DAC to steal fossil-free energy from the grid and slow decarbonization? And if renewable energy is purposely built, how to deal with intermittency when CapEx demand 24/7 usage?
Yeah, great questions. So I'm working with some colleagues at RMI to delve into this in a little bit more detail. But I think that's why this lowering the energy intensity is so important. I would say that we're looking for things that can couple directly to renewables. The level of renewable capacity that we'll need is going to include both of those goals. So decarbonizing the grid as well as providing the energy for direct air capture. And then interestingly, we are seeing some systems that are better able to kind of ramp up and down to take advantage of intermittent capacity. We're also, separately, we look at long duration storage and other technologies that might be able to help balance out renewable capacity to then be applied to direct air capture in addition to grid applications. So those are a couple of the things that we're looking for on the innovation front.
Cool, amazing. Another question. So I think usually it needs to be, it's more a reaction, but it needs to be like the perception that basically the regeneration energy was the highest part of the costs. But your presentation highlights that basically it's almost like the CapEx, which is like the biggest cost reduction driver. And I think that's a bit counterintuitive because we see the systems as being like extremely energy intensive and not see the CapEx as the main cost reduction driver.
So I think just to clarify, that depends on the type of system that you're using. So for the liquid solvent cases, so having just a liquid has 10% of the surface area than a solid sorbent case. And so you need a much larger air contactor, so much higher CapEx from that in particular. But also say that the liquid solvent cases follow the model more of traditional petrochem, so have that much higher CapEx intensity. Whereas the solid sorbent cases tend to be more modular, and energy is still 35% plus of both cases. So still think energy intensity is a key issue across both. But particularly with the liquid solvent cases, the CapEx is critical.
Great, thanks a lot for that. Another one, which is also something we don't hear that often, is the need to minimize water consumption at scale. It's not something that that's often stressed as being a challenge with DAC. Can you maybe expand on that? Yeah,
so I believe with the liquid solvent case, so various types of DAC technologies can perform better in drier or more humid climates. And so sometimes there's things like humidity swings that'll be used to capture the CO2. So it depends on the tech and the conditions, kind of what the water consumption is, but I'd have to double check. But for the liquid solvent cases, I do know that there's massive amounts of water usage on that front. So it's just an important thing to keep in mind and to quantify when evaluating the different technologies.
A last question, which is about how, and maybe that will anticipate a bit and be a good segue into the last presentation. How do you see basically direct ocean capture as emerging also as a related field, and basically does it build into the same type of technologies and approaches? And do you see these fields as somehow sharing some emerging technologies and development, or is it like really two separate fields?
Yeah, absolutely. At the end of the day, a lot of this is taxonomy and just kind of how you're describing it. All of these different approaches are, at the end of the day, just trying to take carbon out of the atmosphere. We are looking at ocean-based solutions as well. So Project Vesta actually just joined our cohort. I have seen some electrochemistry-based ocean CDR plays that leverage a lot of the same ideas and kind of core principles as electrochemistry for DAC. So I think there's some really nice overlap and synergies between the different approaches for CDR across the different folks that we're hearing from today and others who are working on it out in the world.